Hello students, good morning. Our today's topic is vector products, scalar or dot product. Here we see about the vector products. Under that term, there are different important unit terms. The first one is two vectors are added or subtracted. The resultant is a vector. And that term we discussed earlier under the vector algebra by considering the addition or subtraction of the two vectors. If the two vectors of the same physical quantities are in the same direction or opposite in direction, the two vectors may be added or subtracted, but their resultant is a vector. Second important term is if the vector is multiplied by a scalar, the resultant is a vector, but that vector have different magnitude but same direction. For example, if we choose a vector quantity, that is a velocity term, that velocity vector is multiplied by magnitude, that is this is the scalar, that is 2v, or we can say here the 2 meter per second, 3 meter per second, or 10 meter per second with unit, that is the vector term, that is multiplied by scalar. This is the magnitude of the velocity vector. Then that result again is a vector. But that vector term, velocity vector term, after multiplying its magnitude, have different magnitude but same direction. Another term is vector multiplied by a vector is always vector. Here in this topic, if the two vectors are multiplied, then multiplication of that vector is a different term than multiplication of ordinary number. Now, how it is different? The vector multiplication we take under the two possible ways. First one is scalar product or dot product. If the two vectors of two different physical quantities are multiplied, then that multiplication is not same as ordinary multiplication. But how that is different, that we see under the vector product or the dot product. What are the characteristics of the dot product and what is the statement of scalar product of the dot product? We have to see in detail under the dot product of the two vector. Second is vector product or cross product. If the two vectors again having different physical quantities and we multiplied, that multiplication is under the cross product, then its characteristics are different in comparison with the dot product, and how the physical quantity obey that cross product or the vector product, that we discuss in detail under dot product and cross product. Here we see scalar or dot product. Here we choose the two vectors, vector A and vector B. Vector A is one of the physical quantity and vector B is another physical quantity. Such a two vectors are inclined at an angle theta. Then we have to write the statement of the scalar product or the dot product. Now how we give the statement? The scalar product or the dot product of the two vector is defined as the product of magnitude of the two vectors and the cosine angle between them. Mathematically, it is represented as vector A dot vector B is equal to AB cos theta. That dot product results into scalar term. Therefore, what are its characteristics that we discussing here? Before that, we just see here vector A multiplied by another vector B and we take its dot product. Then we get the result, the product of magnitude of the two vector multiplied by cosine angle between them. Means the dot product depends upon the angle theta. If that angle theta is 0, means both vectors are in the same direction. Means cos theta 0, that is 1. We can get the dot product of the two vector is equal to only its magnitude, that is A into B. If the both vectors are same, then simply we write here the A square. Now that term we discuss under the characteristics of the dot product. Second thing we just see here, if theta is equal to 90 degree, exactly 90 degree, vector A is inclined, we write here the exactly perpendicular with the vector B, angle is 90 degree, then cos 90 is cos 90 0, means the dot product of the two vector is 0. Means if angle is in between 0 to 90 degree, the dot product of the two vector has positive magnitude. And if that angle is in between 90 degree to 180 degree, means both vectors are in one direction. Angle is total 180 degree. And if angle is 180 degree, then cos 180 minus 1. And we write the dot product of two vector is negative. Hence, what are the results we get? If the two vectors are inclined at certain angle, the dot product of the two vector has positive or negative magnitude, it depending upon what is the theta. And when the magnitude is 0, if angle is exactly equal to 90 degree. All that term we discuss, these are the characteristics, and how these are the characteristics we are explaining here, that we see. The first characteristic is that the scalar product of the two vector is a scalar quantity. How we prove that scalar product of the two vector is a scalar quantity? Now see here, vector A is one of the physical quantity, vector B is another physical quantity, and we take the dot product, the result becomes to be a scalar quantity. For example, we see the examples here. Now, which is that example? See, one of the physical quantity is vector, other quantity is again vector. Take the dot product of two vector, result becomes a scalar. Here we take that example, like here, if the force is acting on the object. If we say, suppose this is one object, force is acting on that one, then what happens? The object displaces at certain distance. If the object is displaced through the displacement of due to the under the action of the force here, then work is done by this force. Hence, we get work is one of the physical quantity. That work done by the force which is acted on the object, these are the two vector terms. One is which one? Force multiplied by displacement. We get the work. And that example is under the dot product of the two vector. Scalar product of force and displacement, yes, it gives the result work. Hence, work is a scalar term, but it is the product of two vectors. Which product we take? Dot product. F dot S is a scalar term, and that scalar is work term. Another example, power is a scalar term. But how we get the power is a scalar? It must be result of the two vectors. That is, power is a product of force and velocity. How the power term gets force and velocity? Just see. Power is the, we say here, the work done, rate of work done by the object. Means work per unit time. This is the power term. Work, already you know, it is a force into displacement divided by time. Therefore, we write here the force dot displacement by time. Displacement by time, this is velocity term. And therefore, we get power P is equal to F dot V. F is one vector, force, velocity is another vector, and dot product of the two vector gives the result a scalar term. That scalar term is power. Hence, the first term, scalar product of two vector, is a scalar quantity. That we prove here. Second characteristic is that it obeys commutative law. That is, vector A dot vector B is equal to vector B dot vector A. Here, if we interchange the order of the two vectors, vector A becomes vector B and vector B becomes vector A. Then what happens? The dot product of the two vector again remains same. Means vector A dot B is equal to AB cos theta, and vector B dot vector A is again BA cos theta. AB must be equal to BA. That product is multiplication is ordinary. Say here the AB or BA. Result is same, magnitude is same, and therefore it obeys commutative law. A dot B is equal to B dot A. Third characteristic is scalar product is distributive over vector addition. Means vector A dot B plus C. B plus C is one of the vector. That vector multiplied by another vector A, means A dot another vector B plus C. What is the result? Vector A dot B plus vector A dot C. Means this obey distributive law over the vector addition. Third characteristic, if vector A and B are parallel. Now see here, vector A and B are parallel. Then what is the angle between them? Theta is 0. And if theta is 0, cos is 1. Hence A dot B becomes equal to AB. Or if we write the two same vectors, vector A dot vector A, then vector A dot A, it gives A square. Hence the product of the scalar product of the two vector having the same physical quantity, then that result gives, it is the square of its magnitude. That is one of the another result we discuss here. Scalar product of a vector with itself is equal to square of its magnitude. Means vector A dot A or vector B dot B equal to A square or B square. This is one of the result. Another characteristic is that if vector A and B are perpendicular to each other. How these are perpendicular? Vector A is exactly perpendicular, means angle between them is 90 degree. And if angle is 90 degree, then what is cos 90? Cos 90 is 0. Means the dot product of the two vector becomes 0. Hence we write the characteristic, vector A and B are perpendicular to each other. Their dot product is always 0. Theta 90, cos 90 is 0. Therefore, dot product is 0. Now see the another characteristic by considering unit vectors. If I is the unit vector along x-axis, j is the unit vector along y-axis, and k is the unit vector along z-axis. Now then, how we find the scalar product of the two unit vectors? For example, if we write the unit vector I along x-axis, unit vector along same axis. We know that here the A dot A, what is the result you get? A dot A square, or B dot B square. In the same manner, if we considering the product of the two unit vectors, vector I dot vector I, then what is the result you get? We get 1, since these are the unit vector. Similarly, product of the two unit vector along y-axis, j dot j, that is again 1. K dot k along z-axis, k dot k is again 1, using that property. Vector A and B are parallel if theta is 0, means two unit vectors, angle between them is 0, cos 0 is 1. But here we write the unit vector, unit term, unit magnitude along the x-axis, that is I dot I is 1, j dot j 1, k dot k 1. But if the two unit vectors are perpendicular, then what is the result? I dot j, these are the two unit vectors exactly perpendicular to each other. And if these are perpendicular, means here angle between the two unit vectors is 90 degree. Then what result we see earlier? Dot product is 0. Hence I dot j or I dot k or k dot I, or we say I dot k, k dot j, any term we write here, that must be equal to 0. Now we see the next term under the scalar product, next characteristic. If the two vectors are multiplied, then we have to find its magnitude in terms of the rectangular component. Now see here, the scalar or dot product we have to express in terms of magnitude of their rectangular component. For that, we choose two vectors having the unit vector I, j, k along x, y, z axis, and their components of the vector A along x-axis, y-axis, and z-axis are ax, ay, az respectively. Similarly, vector B. Vector B is equal to vector I bx plus vector j by plus vector k bz. What are these bx, by, bz? These are the component of the vector B along x-axis, y-axis, and z-axis. Now, here we find what is the dot product of the two vector. Hence, vector A dot vector B, we take the dot product of the two brackets. Vector A is IAX plus JAY plus KAZ dot vector B. Vector B is IBX plus vector JBY plus vector KBZ. Now we simplify the dot product of the two bracketed terms. How we find? We firstly IAX multiplied by second bracket, JAY multiplied by the same bracket, plus KAZ multiplied by this bracket, and this is the term we write here directly. IAX multiplied by IBX plus JBY plus KBZ, plus this sign as it is, JAY, we take the dot, IBX plus JBY plus KBZ plus KAZ dot IBX plus JBY plus KBZ. Now, we simplify the first term, IX dot bracketed term. For that, we use the earlier identities. Vector I dot I. What is vector I dot I? 1. Vector I dot J, 0. Vector I dot K, 0. Similarly, vector J dot I, 0. Vector J dot J, 1. Vector J dot K, again 0. Similarly, for third bracket, third term, vector K dot I, again 0. Vector K dot J, again 0. K dot K is 1. Using that one, we use the same one, I dot I or J dot J or K dot K, that is 1. And I dot J, or I dot k or k dot I, that must be equal to 0. Hence, direct result of this term we write vector A dot B is equal to AX BX. Since I dot I is 1, AX BX, all other terms are 0. Hence, for first term, AX BX we get. Second term, once we solve, we get only J dot J is 1. All other terms are 0. Hence, we write AY BY plus. For third term, only K dot K is 1. Other two terms are 0. Therefore, simply we write AZ BZ. And that term is represented by this equation, gives the scalar product of the two vector we express in terms of its magnitude. Now see here, if instead of the two different vectors, if we choose the same vectors, then what is its magnitude? Vector A dot A. What is the term you get? AX means it is simply we write the A square, since only one component is there. Or we write the B dot B, it is simply B square. In this way, this is one of the characteristics of the scalar product or the dot product, that is the dot product of the two vector having the magnitude vector A dot B is equal to AX BX plus AY BY plus AZ BZ, or if the two vectors having same physical quantity or the same vectors and their dot product is always equal to square of its magnitude. This is A dot A equal to A square or B dot B equal to B square, and that is the scalar product of the two vector we have to complete it here. Thank you.